Hello, in this problem we're going to be looking at a half-life of a medication. Many times this information is given in the package insert, and for this particular problem we were given different information in the package insert. So it asks us to return to the medication elimination question, question 3, and then to figure out what is the half-life. So let's go back to that question. And here we have all the work that we've already done on that question. So we looked at the change and identified a pattern. We looked at the ratios and identified that it is definitely exponential. And we created actually 3 different models. And we're going to use this model right here because this is an hourly model. When we look at this model, we see that our starting amount was 100. And so to get to half of that, half of 100 is 50. We had done the math looking at the values and how they decreased over the first 24 hours. And so we see that it would be a little beyond the 24-hour mark where we would get to 50. And that is why I'm picking to use the hourly model as opposed to the daily model or the every 4-hour model. So I'm going to take this formula with me to our other slide and work at finding the half-life for this medication. So working here, we have our formula y equals starting amount of 100, decay factor, because this is smaller than 1, of 0.974, where our time is given in hours. Now we could use the NPAT formula and have the n here instead of the y. It doesn't truly matter, knowing that this would be the amount, and knowing from what we copied from the other slide that this is the hours. So when we're dealing with half-life, half-life is time to get to half. So we started with 100. So I'm literally going to divide that in 2, and we want to end up with 50. That 50 is an amount. So I have as my equation 50 equals 100.974 to the t power. We could solve this with a logarithm because we are trying to figure out an unknown exponent, and logarithms allow us to do that. We can also solve by graphing, and today that is what we're going to do. So I'm going to take this and make that my y1, and take my formula and make that y2, and figure out where these two graphs intersect. So we'll go to our calculator. So I'll go to my y equals, clear out my previous work, and I'm looking for when does this reach 50, and my original amount was 100, and I have my decay factor of 0.974, and that was raised to the t or x power. So now I have to think about what would be an appropriate window. So the x or the t is the time. And we had looked at the data before. We saw that it did not happen in the first 24 hours. So let's go up to 48 and think it's going to happen within the first 2 days. And then as far as our values, we started with 100. So I'm going to put that as my maximum. And it was the decay problem. So the values are coming down from there. So I'll graph. And we've captured a good window. We see this red line is the curve describing how the medication is being removed from the body, and this blue line is the half of that original amount. So we'll find that point of intersection, second trace, option 5. Enter for first curve, enter for second curve, enter for guess, and we get 26.3, 1, and 50. So going back here, here is my graph. This axis is my time. We went out to 48 hours. This axis is my amount. We went up to 100. We graphed our line coming straight across at 50. We graphed our curve, and we found that these two met at 26.31, 50. So of those two, the first, the x is my time, the y is the amount. And so when we're looking for half-life, we're looking for time. So the half-life of this is right about 26.31 hours. And so that is the time that it takes for the original amount to decrease by half.